Hello, my name is Herman Neufeld. I'm the technical advisor for TDK, and today I'm gonna demonstrate how to do a simulation with QSPICE on one of TDK's micropole devices. First, we're gonna go through a table here. This table can be obtained from the website. From TDK, and it shows, in this case, the Arctic's Ultrascale FPGA, and the table contains, on the left side, your voltage rails. On the right side, you see the QSPICE model and the transient response plot. And basically what you need is to, if you want to look at the rails, let's take, for example, the VCC aux rail. That says that you have a nominal voltage of 1.8 volts, 3 amps, 1% DC ripple, and the basic parameters that you need are 4 in order to do this sim. And those are the VN, which is 1.8 volts, the output current, which is 3 amps, the load step, which is 100% in this case, and the slew rate, which is 1 amp per microsecond. And then what you do is you can download the QSPICE model just by clicking on that symbol of the zip file and downloading it to your hard drive. And if you do that, I'm going to show you, I already have done that, and once you extract those files, okay, that's the file right here, you would get 3 files. Okay, it's a DLL file, and then these other 2 files here. The one you need is this top file. This is the schematic file. So I'm going to click on it, and that'll start QSPICE. So what you see on your screen is the circuit of the 1606, and that also includes the 1606A. And let's get started. So on the left here, you see the V1, which is the input voltage is 12 volts. And then you have an enable pin. So you want to program this to wherever you want to by using these resistors, and you can get the enable threshold from the data sheet. And once you're done with that, then you go over to the right here, and you see the output capacitor. This is basically what we're going to concentrate on, is this output capacitor, because that's the inductor is already inside, and the capacitor will be the one that you need to select for your design. Now, you see here you have an R top and R bottom. This selects the output voltage. It goes to the feedback pin. And what this program does is already has a statement here, which is called parameter Vout target voltage. And I've set it to 1.8, okay, because that's what we want to simulate here. If you want to change that, you can just go ahead and double click there, left click, and then just type in the voltage that you want to set, and you're all set. Now you have the top resistor, which is 4.02K, and you have the parameter ratio, in other words, the ratio of these 2 resistors, and it calculates what this resistor, the bottom resistor, is based on this ratio. And then you have also, what are you going to plot here? So you're going to want a transient response. And you want to, this first one, according to the QSPICE, I think this first term is ignored, and this is where you're going to stop your simulation. It's at 5 milliseconds, and you're going to start it recording at 0 milliseconds. And we're going to plot Vout and this IN here. This is, I'm sorry, I1, which is your load step. And that current source is your load, and it's defined by this pulse statement here, which I'm going to explain very briefly. So 0 is when you're starting. -3 implies the current, so those who want 3 amps. And according to the QSPICE developer, all the currents go into the node, okay? And here we're going to take current out of the node. In other words, we're going to load this with 3 amps. And this is why you see a minus sign here. Next, you want to specify when you want to start this current source to be switching, and that's at 3 milliseconds. Next, you want to define what the rise time is and the fall time. And then you want to define the on time of this current source and the period. And that's it. Once you have this all set, then you need to just click right here on the run button. And once you do that, you're going to get the run. And you're going to start from 0, as I mentioned. And the voltage, as you can see, starts ramping up here. And once it's settled, then after a while, the current source begins to load the output. And this is what you see right here. This is your current. Now, what we're interested is in the transient response. So what we're going to do is we're going to zoom, and I'm going to take one of these here and zoom on it right there. And you can see here what the transient response looks like. Now, what you can do is you can see, for example, what the DC regulation is. And that can be done by looking at the peak of this waveform here and the peak of this one and subtracting the two, multiplied by 50 and divided by the output voltage, and that's going to give you the percentage of the regulation. And if I click right here, you can have also a peak-to-peak value of this waveform here. And that's going to give you the AC regulation, right? So you see a peak-to-peak value of 55.9 millivolts. This is given in volts, by the way. So you take this number here and multiply it by 50 because it's plus minus, and you divide by the output voltage, which is, in this case, is 1.8 volts. Okay, you can see it's right there. Now, you may want to add the grid by doing this, right-clicking on the mouse. And you can also, let me see, you can, okay, what you want to do too is you want to see what the ripple is here. For example, you zoom in right here where the ripple is more or less stable, and you can see the ripple right here. And if you go to the left, you click on V out and you do Control right mouse click, and you get peak to peak. You're going to get the peak-to-peak voltage right here, which is 4.2 millivolts. Now, what we do is we take this information, I put it into a plot, okay, by doing a screenshot here. And this is what you see on the table right here. So if I click right here, it's going to open that file and show you the screenshots of the waveforms that I generated. Now, I've generated here several waveforms. One is with a 50 microfarad load. Okay, the AC regulation is this, and the DC ripple is 6.2. And this, by the way, is taken from here, from the bottom statement here. You can read it off. And then if I move down, you can see, again, this is a current here. You can see it has a slew rate is very slow. It's 1 amp per microsecond. And here you have the transient response and the ripple. And you can see how it's improving as I increase the capacitance. And I have 3 capacitors. 500 microfarads is the last one. And you can see that your regulation is really down to 0.58%, and the ripple as well. And also, what I have considered is that the series resistance of the capacitor is 1 milliohm. Okay, it's written right here. ESR equals 1 milliohm unless otherwise noted. But the last plot is with 0.1 milliohm. And you can see that the regulation really didn't change that much. It went from 0.58% to 0.57, which is expected because that's depending on the capacitor. But your DC ripple went down significantly because of the low ESR. And you can see the waveform right here. Okay. And if I go back here, you can see how you can set the series resistance of this capacitor by clicking right here. This statement is the ESR. If you have a problem with the simulation breaking down along the way because maybe collapses, the output doesn't settle, you may want to play with this capacitor here. This is a fast forward capacitor for the output, and my experience is that if you increase this capacitor, then you would improve the stability of this whole thing. Okay, normally you shouldn't. The output in real life will not break down on you, but we're dealing here with a simulator, and there's some bugs to be resolved. This is a new program. The other thing is that the DC load doesn't really play a major role here. Now this is 100% loading, so I've made this resistor here 1 gigaohm. If you want to put a DC load, you can change this resistor to whatever you want to. Just make sure you don't exceed the capability of this part, which is 6 amps. So that completes the simulation, and as you can see, you can find what you need right here. They're all condensed into this table. And once you click on this, you can just see what suits you best for your design. And if that doesn't suit it, then again, you can download the model and you can change the parameters as I showed you right here on this circuit. So thank you very much for watching and look forward to hearing from you. Goodbye.